Hi, my name is Austin Mercado, and I am accompanied today by Nick Olin and Ryan Barsa as we present our Petty 3085 production project. In today's presentation, we will cover a case study of the Tortuga deepwater oil field and discuss different development scenarios. The different scenarios tested will allow us to assess and configure an optimized subsea production system. We were given basic information about our reservoir such as PVT, reservoir, well, and network configuration data, although no production history is available. One of our main goals is to generate a pressure profile for our base case scenario. In addition, we will create production rate first time and cumulative production rate first time for all of our different development scenarios in order to compare and discuss the field operator profit over 10 years production to our base case scenario. Our different scenarios consist of base case, higher or lower separator pressures, larger and smaller idea of wellbore radius, different choke openings, and different types of completions. By establishing this base case model, we will be able to see changes in the performance of our system. This model consisted of two near vertical wells that were drilled at 18,250 feet measured depth with a wellbore radius of 6 inches. These two wells were connected to a manifold using 200-foot jumpers with an ID of 4.5 inches. Once connected at the manifold, the fluid will then be transported through a 5-inch dual flow line to our platform. This dual flow line will cover a horizontal distance of 12.68 miles along the seabed until finally reaching its destination at the platform. The platform sits at 82 feet above mean sea level and is where the dual flow line will connect with our separator. This separator operates at 500 psi and has a maximum liquid handling capacity of 10,000 stock tank barrels per day. The assumptions and calculations that we will refer to during this presentation are oil gravity, gas-oil ratio, skin, area which we use to calculate the external radius of our reservoir, time to reach pseudo-steady state flow, bubble point pressure, relative oil permeability equal to reservoir permeability, anisotropy equal to 1, and pseudo-steady state flow was considered for the entire duration of the well life due to a 65-hour period of transient flow being negligible. Given the following parameters and characteristics shown, a model of the production system was constructed as our base case scenario. The basic PVT data was given: gas-oil ratio 900 standard cubic feet per stock tank barrel, oil gravity 30 degrees API, gas gravity 0.7, and formation water specific gravity equal to 1.1. To establish our fluid model, two key parameters were used: gas-oil ratio and oil gravity. Since our oil gravity was 30 degrees API and our gas-oil ratio was 900 standard cubic feet per stock tank barrel, the black oil model is appropriate for our case. Using the black oil model, the missing data obtained was the viscosity, oil volume factor, and total compressibility. Also, additional assumptions made were anisotropy equal to 1 and relative oil permeability equal to the reservoir permeability. In addition, calculations were done in order to obtain other missing data needed. These correlations and calculations were done using Appendix B in our textbook Petroleum Production Systems. With this data, we were able to conclude on the fluid model that we were going to use. Other important data given was the reservoir and completions data as shown in this chart. Some key parameters to take note of are the permeability equal to 600 millidarcy, the initial reservoir pressure equal to 13,000 psi, and the pressure drawdown equal to 0.2 psi per year per barrel per day after pseudo-steady state flow is established. The remaining data calculated was the skin and external radius of our reservoir. With all of our data and parameters calculated and correlated, we began the building of our model. To do this, we used PipeSim 2013, a multi-phase flow simulator which is used to overcome flow challenges and production optimization. Next, Ryan will show you how we constructed our model in PipeSim.
As students, we were faced with the challenge of simulating the conditions previously described. We had the option of either using a VBA code in Excel or learning how to use PipeSim. Our team decided to use PipeSim due to the ease of varying parameters and visualizing these changes. PipeSim is broken up into two major components, the well and the network. We started with the well component, which constructs your production system from the reservoir to the wellhead. To complete this component, we inserted our casing, production tubing, and packer. Following the installation of our tubulars and packer, we entered our values from the deviation survey in the Tortuga wells. Last, we implemented our open hole completions. The completion tab consists of three sub-tabs: reservoir, skin, and fluid model. All values corresponding to the reservoir were entered, and we established our fluid model as black oil. In order to form open hole completions as requested for the base case scenario, we set the rate dependent skin to 0 and input our calculated skin value of 3.02 in for mechanical skin, completing the well component of our model. Following the completion of the well component, we began building the network component of our model. From our wellhead, we connected to our choke via our 200-foot jumper. Next, the choke was connected to a multiplier, which multiplies all components before it by 2. This simulates two wells of the same parameters before the manifold. We connected the manifold to a sink using our dual flow line. We utilized the sink as our separator because its outlet limits our production to 10,000 stock tank barrels per day and 500 psi. This is the same conditions given our separator in the base case scenario. Following the manifold, we installed a dual flow line and implemented the seabed profile with the data given to connect to our sink. As you can see in the seabed profile, there are some parts of the flow line that are more vertical and some that are more horizontal. This leads to complications in calculating the pressure drop in pipes. Two different methods are used in this situation for more accurate results. For near or completely vertical pipes, Hagerton and Brown is the most accurate method, whereas for most other cases, Beggs and Brills is an accepted method. The threshold you use for this angle to switch from one method to the other is somewhat subjective, but using 70 to 80 degrees is a safe assumption for the angle threshold. Our base case model is now complete. Next, Nick will go over our graphs to explain the results we obtain from running our simulations in PipeSim.
The first graph we're going to look at is the pressure profile of the subsea system. As a fluid particle moves from the bottom hole up the well bore, through the choke, into the manifold, up the flow line to the surface separator. The steep decline in pressure represents traveling up the wellbore, and then the near vertical line represents the pressure change crossing the choke. The multiple plots you see here represent the pressure drawdown characteristics as the well depletes in 3.75 years. Here we're looking at the cumulative production versus time of the base case scenario. As you can see from the graph, the black line is oil, and we produced the full 5 million stock tank barrels of oil in 3.75 years, as well as 4.5 million MSCF of gas and 500,000 stock tank barrels of water. This is the first variant from the base case. We're looking at cumulative oil production versus time as the wellbore radiuses change. We have 3 inches to 12 inches, with our base case being 6 inches. As you can see from the graph, our cumulative production maximum nor our cumulative production profile changes, and the time is the same in the base case. This graph represents a change in the height of the completed zone in the producing reservoir. The base case represents a full completion of 80 feet, and we used intervals of 10, 30, and 50 feet of completed reservoir surface. At the low end of 10 feet, it only extended the life of the reservoir by 0.05 years, which is approximately 2 weeks. This graph represents how choke positions affect the total cumulative production times. As you can see, every case was a complete drawdown of the 5 million barrels, but the times varied differently. At the low end, at a choke opening of 20/64 of an inch, the reservoir was able to deplete in 2.38 years, whereas a choke opening of 10/64 of an inch represents a 9.68 year extent. This final base variant represents a separator pressure change. We chose values of 14.7 ranging up to 1500 psi at the separator. As you can see from the graph, little to no change has been made to the producibility or extent of the producible time of the reservoir. Here we have the first of the IPR TPR graphs. The multiple lines represent the beginning pressures of each year as the well depletes. The near vertical line on the far left represents the TPR curve, and we will investigate that in a moment. This graph is a zoomed section of the previous graph that represents the TPR of the base case system. As the change in flow rate as the well depletes represents a change of 342 stock tank barrels per day. This graph represents the IPR and TPR curves as the separator pressures change. As we can see from the graph, the IPR curves are not changed drastically from the base case scenario as separator pressure changes, and very little effect is resulted as the well draws down in the 3.75 years. This graph represents a zoomed focus of the previous graph to show the TPR has changed very little from the base case scenarios. This graph represents the IPR curve changes due to wellbore radius. As you can see from the graph, there's very little deviation from the base case scenario. Absolute open flow potential has changed just slightly. This graph is a zoom version to show the TPR of the previous graph, and as you can see, the TPRs are identical in all wellbore radiuses. This graph shows the IPR versus TPR as the various choke positions we discussed earlier. As we can see, we finally got some TPR deviation in our graph. This plot represents a zoomed focus on the TPR from the previous graph, and as we can see, we have distinct flow potential differences at the different choke openings. These differences represent a flow rate of 783 stock tank barrels per day to a maximum of 3,082 stock tank barrels per day at a choke opening of 20/64 of an inch. This graph represents a change in the perforation height discussed before. While the perforation height may not greatly affect the depletion time of the reservoir, it has a large margin of change in the absolute open flow potential of the reservoir. This is a zoomed focus to show the TPR of the previous graph. Similarly, the flow rates change very little due to perforation height changes. Here we see the IPR-TPR curves of tubing changes from 1 to 6 inches. Here we have a zoomed focus on the TPR of the previous graph. The pink line on the left represents a 1-inch tubing diameter, while the 2 through 6-inch tubing diameter lines all cluster to the right. As you can see, anything beyond 2 inches does not show great gains in tubing flow potentials. This graph also highlights the downward sloping TPR curve in the leftmost region, where the fluid flow is dominated by gravity, and then the upward sloping portion to the right as the fluid flow mechanics are dominated by friction. This is a further refinement of the previous graph, and as you can see, the 1 to 6 inch diameter range does not become a major factor until you get below 2 inches. From 3 to 6 inches, the TPR curves and the corresponding flow rates are very similar. This graph shows the relationship between a 4-inch flow line and various sizes tubing from 2 to 6 inches at different choke positions. It's important to note that the maximum flow is 6,200 stock tank barrels per day on a 6-inch line and a minimum of 5,400 barrels per day on a 2-inch line. This graph is identical to the previous one, except that it's a 10-inch flow line. It's the same tubing range of 2 to 6 inches, and as can be seen from this graph, the Q max in the 6-inch line is nearly identical to the 6,200 stock tank barrels per day, and the 2-inch line represents a 5,400 stock tank barrel per day production rate. From these two graphs, we can see that the difference between a 4-inch flow line and a 10-inch flow line is negligible, and anything above 2 inches represents almost no increase in production. This graph shows a tubing range of 2 to 6 inches versus various choke positions and the corresponding production rates. As can be seen from the graph, anything beyond a 4-inch tubing size gives negligible increases in production rates as choke position increases. As can also be seen from this graph, anything less than 4-inch tubing only affects production rates when the choke is open greater than 16/64 of an inch.
In conclusion, for the base case, the system is already producing near the separator volume limits at about 5,000 barrels per day. Given dip in the dual flow line profile, slug flow regime is very likely and needs to be accounted for as a safety factor. Also from our simulations, we concluded that the tubing and flow line do not seem to be limiting factors. In addition, the reservoir is depleted by 2 wells in approximately 3.5 years, but there are some real-world problems that must be addressed. It is not realistic that this reservoir will obtain 100% sweep efficiency. Also, tubing velocities are extremely high, and therefore erosional velocity factor needs to be considered more to protect the integrity of our production equipment. Likewise, sand production and collapsing of our wellbore are particularly likely with such high depletion rates and pressure drawdown. In recommendation to account for some of the concerns, producing this reservoir from a single well should be highly considered. If you take into account the price of barrel of oil today, and the max gross income on this investment is about $200 million. If the cost of one offshore well is about $25 to $50 million or more, using one well and extending the depletion rate to nearly 7 years will increase profits substantially. More so, all platform components at this rate can be downsized due to the lower production, considerably reducing the cost of the equipment. Through this case study, we encounter many challenges, one being the learning curve of the software PipeSim. Ultimately, the case study has brought to light the practicality of what we have learned in our petroleum productions class.